Good afternoon and welcome to At Yale Live. I'm Eric Gershon. Our guest today is Yale astronomer Debra Fischer, who studies and searches for planets far outside Earth's own solar system. She will be discussing today how she goes about her work. We'll be taking some of your questions. And Debra, we're glad to have you here on aqueous planet Earth.
That's right.
My first question for you today is, could you define planet for us? I don't think everybody really understands what a planet is.
Right. Well, I think the simplest definition is that a planet is an object that circles a sun, but it gets complicated because there are also moons that circle the planets, and because we had Pluto in our solar system, and the International Astronomical Union defined Pluto as not being like the other planets in our solar system, but being more like the Kuiper Belt objects that are outside of our solar system. In other words, one of hundreds of other objects that are similar to it. So there's an additional constraint that they added, and that is that the object that's a planet has to be large enough that when it's forming in a disk of dust and debris, that it clears a gap as it's going through. And we don't think that Pluto did that.
Now, astronomers study all aspects of the universe, stars, galaxies, black holes. How did planets become your thing?
Well, I was actually finishing graduate school just as the first exoplanet was discovered. And my PhD thesis was on spectroscopy, and that's the technique that was being used to find planets. So, really I feel incredibly lucky. It was partly being in the right place at the right time, quite literally. So, just luck.
And you used the term exoplanet, and
Right.
correct me if I'm wrong, but that's a planet, that's almost any planet outside of our own solar system.
That's right.
Okay.
It's short for a contraction of extrasolar planet, so outside the solar system.
Gotcha. So how are these planets that you study, these exoplanets, how are they different from the planets in Earth's solar system?
Well, that's a great question, and it's one of the things that we were most interested in, because the first planets that were discovered were very unlike the planets in our solar system in the sense that, maybe they had similar mass, for example, to Jupiter, and similar density, but they were in orbits that, were not 12 years long, but were 4 days, hugging their stars. So that was a real surprise, and it really threw us for a loop. We had to think about the interpretation of our data very hard with that one. So I think the one common thread, the one thing we've discovered is that planet formation is a chaotic process. There's one thing that rules, and it's gravity. So you start out with a disk where the planets are forming around the star, and there are thousands of wannabe planets that are collecting debris and matter and building up. And then they gravitationally interact with each other. And you end up with whatever kind of a solar system I think is gravitationally stable is possible, and that's what we're seeing.
Do many of the exoplanets that you and others have found resemble in any significant way the planets in our own solar system?
Well, the characteristics that I like are, first of all, we're finding many multiple planet systems. I think that's the rule.
Pairs almost?
Well, we find 2, 3, 4, 5, 6, 7 planets orbiting a given star. So that's a characteristic that's similar to our own solar system. And we're finding a range of masses that go sort of from Earth-like in their mass and maybe their composition or their density, all the way up to Jupiter-like. So they kind of span that range.
And naturally, it's hard to think about other planets without wondering, as one of our viewers, Kevin, emailed us to ask, do you think it's likely that there's life on other planets? And if there is, how will we recognize it?
Right. Well, okay, so that's why we're all in this business, okay? We're not actually, finding planets is a great bonus. We want to understand, how planets form and how our solar system formed. But I think that, and we all were sort of quiet about this in the beginning, because there had been a lot of kickback, against SETI, the Search for Extraterrestrial Intelligence, in the 1990s when the small program of federal funding was canceled. So we were all sort of quiet about the fact that we're looking for planets because we're looking for platforms for life. And so that's what drives us. And do I think that there's life elsewhere? I don't see how there cannot be, actually. Do I think it's like us, technological? there I think the odds probably go down, so it might be very small numbers, but it's not inconceivable that somewhere else in our Milky Way galaxy, which is comprised of something like 400 billion stars, there's another civilization asking similar questions, or has asked in the past, or will ask in the future. Similar questions that we're asking, are we alone?
So to the extent that you can separate your scientist self from your person self,
Right.
Is what leads you to believe
Right.
that as a scientist that there might be life out there?
Right.
Other life.
So the first thing is that when we found the first multi-planet system, it was around the star Upsilon Andromeda. There were 3 planets orbiting that system. And it was in 1999. I remember walking across the campus, looking at the data and thinking, wow, this really suggests that planet formation is a robust process, something we didn't know. In 1990, for all we knew, stars could form without any planets. Okay, that was the facts. We just didn't know. And now we're seeing this incredible bounty of planets and multiple planet systems. And at exactly the same time, I was listening to the biologists who said, wow, wherever we find water on this planet, it doesn't matter if it's miles beneath the surface of the Earth, you know, or it doesn't matter how acidic it is. If we find water, we're finding life. And if you put those two ideas together, it's kind of hard to imagine that life didn't spontaneously, you know, arise somewhere else. I think one other quick comment is that when we look at other stars and we look through our own galaxy or other galaxies, we see that the galaxies are glowing with molecules called polycyclic aromatic hydrocarbons. These are components that can make up amino acids. So it's not even that life could arise, but it might be so exotic we wouldn't recognize it. I would bet $100 that it's carbon-based life, and that, you know, eventually we'll find it'll be very different from what we are, but, you know, there will be some similarities. There'll be some commonalities.
Let's talk a little bit about how astronomers go about finding planets that they can't see, that are so far away
Right.
that they can't be seen even with the most powerful telescopes.
Right, right. So we have to look at the effect. Well, there are, of course, now several techniques. The technique that I use is sometimes called the wobble technique. And we're watching the star itself, and we map out the velocity of the star as it orbits a common center of mass with the planet. Now, if you think about, you know, the mass of the star is huge, the mass of the planet is tiny. So the common center of mass is often inside the radius of the star. The star is executing, you know, a very tiny orbit. But we map that out, and we then infer the presence of a planet that we can't see. Okay, so that technique, that description, might leave you skeptical, and it left most astronomers skeptical until 1999 again, when we said, okay, but if we're right, and our data, we're really seeing dynamical motion of a planet being of a star being tugged around by a planet, then we will eventually see a planet that passes across the face of its star. And when that happens, the starlight will dim just ever so slightly. And we can tell you at exactly what time that will happen because we understand the orbital parameters. And so we made a prediction for every planet that we found, if it's going to transit, and that was we didn't know the if, okay, because one orbital parameter was missing in our analysis. But if it did, you know, it would occur at exactly 9:35 p.m. And so we had our friends who were measuring brightnesses of stars. They would look at our target star, and they'd look at 4 other stars. And sure enough, one night, you know, in late 1999, one of the stars dimmed just within 30 minutes of the predicted time.
So it's a reproducible thing,
It's very reproducible, yeah.
We have a question from the public, David from Carleton College, emailing us to ask you to elaborate a little bit and maybe suggest well, let me just ask the question. David's question, could some irregularities in celestial orbits be due to small errors in the theory of general relativity instead of due to supposed planets?
Right. Well, rather than the errors in the theory of general relativity, I would say that there are certainly going to be general relativistic effects that need to be accounted for in very precise orbit measurements. And so we've done this, for example, with Mercury in our own solar system. But we're very close to Mercury, and we get an incredibly precise, measurement of its position. So we can measure that general relativistic perturbation of Mercury, but it's at such a tiny level that it's not yet important for most of the other planetary systems that we're looking at. But sure, we're watching all the time what else could be going on in the system.
So you've got two techniques that you can kind of use, one to verify the others,
Exactly,
is the general idea.
Exactly.
So when did this hunt for exoplanets really heat up? When did it get going?
Yeah, it's been going for probably a century.
Oh.
And most of the attempts to find planets were failures. In the 1950s, Otto Struve predicted that, if you use the radial velocity technique, you should be able to get down to a high enough precision so that you could at least detect Jupiters that are close to their stars if they existed. And of course, astronomers thought that's ridiculous. Hot Jupiters are not going to be close to their stars. But the idea was right, and people kept pushing and pushing. And, things really started to heat up, as you put it, in, the late 1980s when Dave Latham at Harvard discovered a brown dwarf orbiting its star. And then in 1995 when Michel Mayor and Didier Queloz, Swiss astronomers, discovered a planet like Jupiter orbiting a star that's very much like our sun. And then as soon as that system was detected, there was like an aha moment where we said, oh, we thought these planets would be in 10-year orbits. Who thought they'd be in 4-day orbits? And you start looking at the star differently. Instead of taking 1 or 2 observations per year, you have to take, an observation every night to detect those close-in systems. So we changed our strategy. We adapted once we found the first planet. And suddenly, they began to pour out, so that now there are hundreds with the Doppler technique and thousands from the Kepler mission.
And if I'm not mistaken, there's a program here that Yale participates in called Planet Hunters.
Oh, right.
Which actually allows the public to participate in the discovery of planets. So could you tell us a little bit about that?
Right. I'm so excited about this project. This is a project that we started with some colleagues at Oxford University. The people at Oxford had set up a whole series of citizen science projects like Galaxy Zoo. And one of the postdocs here, Kevin Chawinski, kept asking me, can we do something with exoplanets? The public loves exoplanets. And I think about it and say, yeah, I just can't think of really how we can bring the public in until I saw the Kepler data, from the NASA Kepler mission, which is measuring the brightness of 150,000 stars and looking for tiny little transits as the stars go in front of as the planets go in front of the stars. So we put together a website, planethunters.org, which serves up the Kepler light curves and has the public look at the data and say, first of all, does the star look, is it fairly constant in its brightness, or is it changing?
Let me interrupt you just briefly. So when you say you have the public look at the data, are they looking at numbers or are they looking at visuals?
They're looking at a graph.
Okay.
And we were really worried about showing people a graph, right? That, and I tested on some high school students and friends, but we made it, I think, visually appealing. And anyway, the proof is that we now have over 170,000 users. They have collectively put in an amount of time assessing Kepler light curves that is mind-boggling. Just as background, when I ask people on the Kepler team, they say, oh, I look at the light curves all the time. That's really the way to go. Yes, we have computer algorithms, but I spend so much time. And I say, okay, add up the amount of time that you think you've spent over the last 3 years and make it run a cumulative total. So 24/7 you do nothing but look at light curves. What do you think it adds up to? And they'll calculate, I bet it's 3 months, or I bet it's 4 months. Well, the 170,000 Planet Hunter users have 24/7 put in a cumulative total of more than 300 years. 300 man-years looking at light curves.
And these people are all over the world?
All over the world. All over the world.
Have their contributions led to the discovery of new planets?
They
exoplanets?
absolutely have. Of course, they've detected most of the planets that the Kepler algorithms are finding. Kepler has computer algorithms that search through the data because the amount of data is just overwhelming. It's just incredible. But they've also, we've published now 4 papers, and the first discoverers in the public for those systems are co-authors on the paper. And these discoveries have helped the Kepler team, because the Kepler team says, wait, why would we have missed that? Right? And they go back and they tune up their algorithms, or computer algorithms, so that their algorithms are more efficient.
And again, these are primarily lay people, perhaps lay people with, I mean, surely with a strong interest in astronomy, but these are not professionally trained astronomers for the most part.
Right, and you know, I would say even a lot of people aren't sure what they're looking at, but they're still finding things. And what is developed on the site, that's the most useful thing of all, is a sort of a cadre of super users who are actually incredibly good amateur astronomers. And they're very generous with their time, and they're bringing the newbies along, and you know, helping and putting together collections, and you know, and really making the site quite powerful.
So how do professional astronomers make use of the contributions of the lay astronomers?
We can hardly keep up with them, and so we've developed a second layer to the site. You know, the users, we now have an extraction algorithm which decides which votes are the votes of the public are actually weighted. And the way that we do this is we actually drop in fake transits. We know exactly what the depth and the orbital period is. And as people recover those, then we get an assessment of, you know, how complete their analysis is for different ranges of planets. So in any case, what we're doing is extracting then the public's best guesses for transits, and we're moving them to a site which we call Second Look. And we give our 3,000 most dedicated Planet Hunter users access to Second Look. So they then do a double check, sieving through all of that data, and then it comes out, and we then, the professional astronomers, are spending time looking at the light curves, going to the Keck Observatory and collecting more data to follow up, and you know, analyzing the stars, all sorts of things, and writing up the papers.
Let me take another question from the public. Mike emails us to ask, and this is getting back to the topic about life, the potential for life on other planets.
Right.
If there is life on other planets, should we try to make contact with it? And that isn't really an astronomical question.
No, it's a philosophical. Yeah, exactly. I think, unfortunately, we don't have much choice. If there's life, imagine like that there was another civilization on a nearby star. If it were like us, right, and broadcasting TV signals and radio signals, we would have discovered it already. Whether they wanted us to or not, those signals would drift past us. And so our signals have been drifting out over time for the last 50 years, 50 plus years now. And so all stars that are within 50 light years, and that's, you know, hundreds of stars of our sun, could have the option of detecting our signal. So we might not have a choice. And what we're really looking for, I think, when we think about technological life, technological civilizations, are serendipitous discoveries. Eventually, we'll want to harness the energy from the sun. So we might build something called a Dyson sphere that essentially encompasses the sun as a sort of a grid, collects power, and then channels it back to our planet. If you do that, then it could affect the spectrum of the sun. It might change the color of the sun in some way for another observer. So we're looking all the time in our data for something that just doesn't seem right. Yeah.
Pluto.
Yeah.
Planet or not planet? And what did you make of Pluto's demotion as from the status of planet within our own solar system?
Yeah, I see it as science in action. This is the way science goes. We build a theory that describes, you know, and also, right, our whole convention for naming a planet. Pluto doesn't care if we call it a planet or an outer solar system object, but we care because it helps to define our understanding of what a planet is. And so I think from that aspect, I think it was pretty brave of the International Astronomical Union to go up against all those kindergartners and say Pluto is not a planet. There was a lot of kickback, but you know, it was the right thing to do. Pluto doesn't look like the other planets in our solar system.
Let me ask you about sort of how close the nearest exoplanets are.
Right.
Are any of the planets outside of our solar system places that humans conceivably could travel to?
Right, good question. Okay, so first of all, the first thing to make clear is that I said before, our galaxy right, is this enormous disk that has, 400 billion stars and then globular clusters sort of in a spherical distribution around it. But all of the planets that we are finding, that the Kepler mission is finding, they're all in a tiny little bubble around the sun, okay, that's inside of the Milky Way galaxy. So we're not looking or detecting planets in other galaxies, right? Those are completely virgin, that's virgin territory.
Wow.
So we're just talking about our little tiny neighborhood. And yet we're finding all of these planets. So, sorry, what was your question?
Well, so the question was, are there exoplanets that human beings conceivably
that we can travel to? Okay,
Yeah.
so I think the closest star that we know has planets is about 15 light years away.
Okay.
We're looking very hard at the Alpha Centauri system right now, which you can see from the southern hemisphere. It's 4 light years away. Okay, will we go there? That's actually hard for me to imagine unless physics changes, unless, it would just require an incredible personal commitment to travel for 40 or 100 years, right? And have your future generations be committing them to space travel. But what we will do is we will start, as technology advances, I imagine that we will be sending little bots, and the perfect model is your cell phone. You accelerate your cell phone to 10% the speed of light. It gets to the Alpha Centauri system in 40 years. It takes pictures, opens up, right, takes pictures, and it phones home, sends the signals back, and the travel time for that radio signal is the speed of light, so it's only 4 years to get back. So that kind of thing, I think, will start happening.
That is something to think about.
Yeah.
Debra, thank you so much for joining us today. I can't believe the time has flown by, but
pleasure,
it has.
Yeah.
And it's been great fun, and we'll hope to talk to you again.
Sure.
Thanks to all of you very much for watching At Yale Live with Debra Fischer, Professor of Astronomy at Yale University. Thanks very much. Join us again at the end of the summer.
All right, thanks. It was fun.